let's see. Yep, so I'm going to talk about massively parallel databases. So you saw a couple massively parallel databases in that slide. Redshift is an obvious example. Greenplum's another one. Yeah, so I work at DataZoo. We're also in the ad tech space. We have a pretty big data problem. We have about half a petabyte of data in our Hadoop cluster right now, and we have 3 100 plus terabyte Greenplum clusters that we're running currently. And so what I'm going to cover today are a general motivation for MPP databases and a comparison with some of the other big data options that you have. I'm going to talk a lot more about the theory of MPP databases, and then towards the end, if we have much time left, we'll go over some usage tips. So to start with, let's see. OK, how big is big data? For the purposes of this talk, we're going to say bigger than a single Postgres, more than you can fit in a single traditional database. I put 1 to 2 terabytes on here. That's probably a little low these days. You can probably push a Postgres or a single node Oracle server a bit past that. But once you get past that, you're going to not be able to have a single machine storing all of your data. And at that point, you need to find some way to parallelize your processing. There's a couple of different options. MapReduce, you saw Hadoop on the Digitas slides. That's a big one. And that sort of MapReduce goes along with HDFS or some sort of distributed file system that distributes the data out across multiple machines. The other solution, you've got your NoSQL solutions. I'll put a slide up about those, but like MongoDB, where you, instead of using a traditional database, use a key value store. I'll talk a little bit about continuing to use traditional databases, but sharding, and then we'll go deeper on MPP databases. So first up, MapReduce. There are a ton of problems for which MapReduce is definitely the right solution. It has some advantages and disadvantages. One of the advantage/disadvantages is it's schemaless. So if you're doing a text analysis problem, then the lack of a schema is actually an advantage. If you have an ad tech attribution problem where you know a lot about the schema of your data, the not having that information available to you is a detriment. So some vendors, Hadoop, MapR, and you can put SQL support on top of that. So we mentioned Hive already, and that's putting a schema layer and a simple database layer on top of the schemaless HDFS MapReduce solution. That can be a good way to allow not super technical users access to your Hadoop cluster. They can write SQL queries, which is a lot more common than people who can write Java MapReduce jobs. But the latency is going to be pretty high compared to a traditional database. You can't put even an asynchronous web front end behind it, because your query times are going to be, best case, in the seconds, and they're going to go up from there. So if you need something that can respond to simple queries in sub 1 second times, it's just not really possible to do that with Hive. I think Impala's a little better, but still I would be iffy about that. So another option for big data is NoSQL. That is sort of a move away from the DB features, sort of by design. It uses key value stores, which make it easy to scale across multiple machines. It's not required for a NoSQL solution to run on multiple machines, but it's a lot easier for a NoSQL solution than a traditional SQL solution to scale across multiple machines, multiple servers. But it's not a relational database. So you have the same problem of it's difficult to give SQL access to an analyst who's used to SQL but is not comfortable with programming. And you're moving some of what's traditionally database processing into the application layer. Like in order to provide concurrency controls and transaction type controls, it's harder to do that on multiple machines in a NoSQL solution. So you're pushing some of your application logic into a different location. It's not necessarily a good or a bad thing, but it moves you away from traditional database processing and where the different roles and responsibilities generally lie. So back to more traditional databases. One option that's a pretty common one is sharding. And the idea there is that you just split up your data. Instead of having one database, now you have 2 or 5 or 10 databases. But you divide the data that lives on those databases based on something. So you could divide by company, right? So maybe you're a parts manufacturer, or maybe you're serving ads to these different car companies, and you just dedicate an entire database warehouse to each of your customers. That can be tricky. You might not have the same amount of data being generated by Ford. Ford might be twice as big as GM and Toyota combined. So you're going to have to play some balancing games to distribute the data out, and you're going to have to keep moving things around, right? So maybe you combine GM and Toyota onto one server and give Ford its own server, but then GM takes off, and now you have to split GM out. You're moving data around. Some companies might have relationships where a single is still too big. Ford just has so much data that even all by themselves, they're too big for a single warehouse. So now you're back to the original problem statement, which is you have too much data to store on even the beefiest, most expensive SQL server that you can buy. And again, you're pushing information into the application layer. Now your front end, your analysts have to be aware of where the data lives. So you have to push logic out of the database and into some sort of layer up from the database, so that can be aware. Just to give another example of sharding, you could shard by date, right? That's another simple one. It saves the company size problem because you can just adjust the date range. Maybe you start by year, and then as your data gets bigger, you shard by month, and then you shard by week, and then you shard by day as data grows and grows and grows. The problem there is your usage is probably not even across all of those shards, right? Most of your writes are going to be in the current month because you've got new data coming in for all of the orders in March or September. So all of the orders in September are coming in, so you're writing to September a lot. You're not really writing to the other databases. And depending on what your analysts are running, they might be querying different. Maybe they're also only querying the month, so you don't get as much of an advantage of really distributing your workload evenly across all of the solutions, or all of the databases. So MPP, massively parallel processing databases, give you a way to essentially shard on a fair function. So what you do is you create multiple segment nodes, multiple databases, each of which is going to do a small percentage of the work. And then you put a fraction of the data. So you have 24 nodes. You put 1/24 of the data on each of those nodes, essentially sharding by the modulus function. And the advantages are you get most of the pros and cons of a traditional database. It's generally, you can have transaction support. You can have index support. They have a full-featured SQL language that's almost fully complete. Hive and a lot of the other solutions have a limited support for SQL syntax. You can't do certain kinds of subselects. You can't do overfunctions. Whereas with an MPP database, you get almost the full SQL query language. There are a couple exceptions. I'll talk about them later. But you get all the pros and cons of a traditional database, pretty much. OK. So yeah, the obvious exceptions to that are it's very hard for an MPP database to enforce foreign keys. So while you can have full schema support and you can define most of the rules that you can define around a traditional database, you can't get it to enforce foreign keys for you. It's pretty expensive. You can build logic on top that will enforce it if you really need to enforce your foreign keys, but that's one major database feature that you just don't get out of the box. And there's some tricks around functions, user-defined functions that also query data, but that's a little bit more subtle. Foreign keys is probably the biggest, most obvious one. So I'm going to put up a quick picture. Imagine this is our 4-node Greenplum cluster. So this is Greenplum. It's a pretty big MPP database. So we have 4 nodes and a master node. Each of these nodes is a pretty big server. Probably at DataZoo, our clusters are 36 node clusters, and each cluster has about 20 terabytes of data available, and you can use between half and 70% of that. So So that's how you get up to 100 terabytes. You need a lot of nodes. But for this instance, we're going to put four nodes up there. The master node essentially pretends to be a Postgres all by itself. So if you have software that you've already installed, or you have a web front end that you want to plug into this Greenplum background, the master node is just acting like a Postgres server. So you have a Postgres server sitting there responding to SQL queries. And it processes those and farms them out to the workers, aggregates the results, and returns the results to the client. So if you're used to using Python, you can point your Python as though you're pointing it to a traditional Postgres database, and it just completely simulates a traditional database for most purposes, which makes it really convenient to plug into an existing workflow. If you have analysts who are used to working with the data a specific way, or maybe they have a package that they're used to using, they can plug in an MPP database pretty easily. So let's look inside each of these segment nodes. When I said that you break it up into multiple databases, you actually break it up into more than one database per machine. Because most database software is not great at using multiple cores. So since we've already solved the parallelization problem to move it onto multiple machines, we just break it down a step further and say, let's put 6 machines, 6 primary nodes, and 6 replication nodes, I'll talk about that in the next slide, on each machine so that each one can be dedicated to a core. So we can pretty much max out the amount of processing that this machine is doing. And if we look inside one of these segment nodes, we see that there are 6 primary nodes and 6 mirror nodes. Another thing you find once you start getting into big database problems is that hardware failures stop being something that you have to design for as an inconvenience, and they become something you have to design for as a daily operational thing. So I said we run 36 node clusters. When we were running, I did the math for a 24 node cluster with 18 hard drives in it. That's over 400 hard drives. So you're going to have hard drive failures regularly. And you need to be able to continue processing when nodes are unavailable for different reasons. And the way Greenplum does this, and I think it's common for a lot of MPP databases, Redshift does it, but you don't see it. They do it sort of in secret on the back end. They only talk about the primary nodes, but they actually build mirror nodes for you. What you do is you have 2 copies of all the data, and each copy is on a different server from its primary. So one of the other nodes that was there has one's data, a different one has 2. You distribute it out so that one of these machines can get knocked off the network, and you can continue to process queries. The master node will detect that it lost these primaries, and it'll promote the mirrors, and they can take over processing immediately because they have full copies of the data. They're ready to go, which allows you to have a lot more resiliency in the face of common hardware failures, which are just a cost of doing business at this scale. Quick digression, I'm going to talk a little bit about columnar databases. They're common in MPP solutions. They're not required by MPP solutions, and they don't require an MPP solution. So you could have a single node columnar database, and you have MPP solutions that don't use columnar databases. Greenplum, for example, allows you to mix and match. You can have row-based tables or columnar-based tables. But they sort of came up together, and most of the major vendors use columnar databases pretty heavily, and they get a lot of their advantages from that. So they're kind of generally associated with MPP databases. Redshift, Greenplum, Vertica all either offer or use only columnar databases. And a way to think about columnar databases is that each column in your data set is actually its own table. Each column is sorted separately from each other column. Whereas in a traditional database, the rows are stored together, you access it through your primary key, and you read it. In a data warehouse, you often have pretty wide fact tables. So as you are processing these rows, you have to, at a minimum, scan the disk over the head of all of this data. You might have, it's not unreasonable to have 50 columns in a single fact table, but you only need 3 of them. So you're moving the head past all of this data. You might even be returning it into memory to determine that you don't need it and then throwing it out. So by using columnar databases, you can really speed up query times, especially on wide fact tables. And the other advantage is that most of these MPP solutions take advantage of compression. We compress the data on the disk so we can store more data in our cluster. And we're also generally I/O bound to the disk. So we trade some CPU processing for being able to pull the data off the disk compressed. And it's actually, you can usually end up ahead by compressing data and uncompressing it on the fly. Seems counterintuitive, especially to somebody who's been working with computers for a while, that you would compress the data just to uncompress it after writing it to the disk and still end up ahead, but you do. So going back to the this slide where we had all of our Postgres databases divided up and each storing the data. I said that it is essentially like sharding, that you're essentially storing a little piece of the data on each of your Postgres nodes. The way that you determine what data goes where is by using the distribution key. You have to pick a key, and you have to say, based on what, put the data in the different places. And so the most common is to pick a key, and then the key will be transferred via some sort of hash function to an integer, and then the integer will be modulo the number of nodes you have, and you put the data on the right piece. And the other option is to distribute randomly or round robin. As new data comes in, just put it on a random node. That's what you end up having to do if you can't find a key in your data that meets the two requirements that I list here. The first is that it has to hash evenly. Each node has to have a perfectly even distribution. Whatever you pick has to be close enough that when you hash it and modulo it, it ends up on an even number of nodes. So if your user IDs are not sequential or are not random, like if they have an inherent bias in them, where more of your user IDs are going to end up on one node than another, you're going to have you can't really use that as a primary key, because the database is going to skew. That node is going to become slower. Your whole cluster is as fast as your slowest node, so it needs to be perfectly evenly distributed. And all of the vendors provide ways to check that your distribution keys are coming out even, that the data is even across all of your databases. And the other thing is, if you're going to join data, large fact tables, together, they really need to be distributed on the same key. You can't have the nodes talking to each other to get huge amounts of data pulled back together. If we have some time later, I'll try to come up with an example of that. The ad tech is an easy place to come up with a place where you have two sets of data that are both very large and need to be joined together. But you can sort of create a thought experiment around, like, maybe student IDs, although usually even the biggest colleges aren't really talking about 100+ terabyte data sets for their numbers of students yet, or ever. OK, so this is what two of the segments on one of these nodes look like. Each has a cut of the data. So in this particular example, we've distributed both of these tables by student ID. So the 46 will always end up on segment 7. Student ID 46 in both of these tables is always going to end up on segment 7. Student ID 99 is always going to end up on that segment 32. And we've got some examples of other segments in there that are showing up. The idea is that every time we see a new student ID, we need to put it in the database. We hash it. We apply the distribution function to it, and then we put it on the correct node. And I'm actually going to put a little code up here. I'm going to give you an example of a create table statement. The first part of this is standard SQL. If you've worked with SQL before, you've seen the create table syntax. And then at the end, you list your distribution key. So here we're just saying distribute by ID. And Greenplum's going to take care of creating all of the tables on the segment nodes and and when inserts come in, put them into the correct table. Another idea related to distribution, but separate from it, is partitioning. And in partitioning, let's think about it at the level of the master node, at the abstracted level. The idea is that you have a single table that acts as an interface to multiple tables where you've broken the data up by pieces. Similar to sharding, except where sharding you create multiple databases, here you create multiple individual tables. And the common use case for this is you've got a large fact table, but I did orders here. Most of your queries are going to be in a tiny subset of that, right? Like people might look at a year's worth of orders or a month's worth of orders, but they're generally not, most of your queries are not all of your orders from the beginning of time to today. So by creating partitions, the database is going to create separate tables, and the query optimizer can quickly prune all of the partitions that aren't related to your current data set, your current request. So as long as when you query this table, you make sure to include the date column in your where clause. If your date column, if you're looking at orders from 2014 in July, it just drops these other two databases, and you don't have to deal with, 2/3 of your data. The query planner can just cut out a big chunk of the work that it has to do by using partitioning. It's not supported in every MPP. Greenplum, Vertica support it. Redshift does not. They have kind of a workaround, but it's not really traditional partitioning as it's thought. Partitioning actually is one of the few features that, beyond being an MPP itself, that came to Greenplum before Postgres. So Greenplum has had this for a while, and Postgres 9 adds partitioning back in for single node databases. So you can have partitioning even if you're not using an MPP, using Postgres these days. An example of some details about partitioning in Greenplum specifically. You define it when you define the create table statement. It actually supports 2 levels of partitioning, so you could have date and then customer. You could partition first by date, so you'd get one table for each year, and then you could subpartition that by a table under that level for each client. That works. It's theoretically supported. The problem with that is simple math. If you partition by month and then you partition by all of your customers, you're going to end up with hundreds of partitions, which then really becomes a problem once you add in the columnar database, because each of your columns is also sort of its own table. And pretty soon you're dealing with file handle numbers in the tens of thousands. Your query planner slows down, and it's not great. So there are solutions where 2-level partitioning makes sense, but in almost all practical cases, you need to keep it. 1 is going to be the maximum number you can have. And we'll go through this quickly. It's just in addition to the distribute by, now on an MPP database, you can also partition by. And there's, we're partitioning this by date, and we're creating one for every month. The important gotcha there is that's exclusive. So on January 1st, 2015, all inserts to this database are going to start failing. You won't be able to put data in. It's going to reject all of your rows. So one of your common maintenance tasks has to be to keep ahead of your partitioning strategy. Make sure you're partitioning by the end of the year.
Does any of this done automatically, or does the DBA?
So the DBA has to, so the question is this done automatically? And the answer is that this has to be set up when you create your table. The DBA or the engineer who's building this has to set up the partitioning. And yes, and so there is, as far as I know, none of the MPP databases offer a tool that says, around December, create next month's partitions, for next year's partitions for me. Somebody has to, I mean, you could build something in cron, but you're more likely you're just going to have a reminder on your DBA's Google Calendar to log in and fix it. There's definitely quite a few differences, but they all generally use this sort of theory of partitioning, I believe. They're all sort of MPP databases in the sense that most of what we've discussed today applies to all of them. I'll talk a little bit about their differences. I can talk in depth about Greenplum's differences, because I've worked with Greenplum quite a bit. When we get to Redshift, and especially to Vertica, I'm going more on a little bit of proof of concept code we worked with and what I've read on the internet. So feel free to correct me, especially when we get to Vertica, if I get any of those details wrong. Partitioning in Vertica, it is supported. As I just said, I've never dealt with this in person, but the opinion of the experts posting on the internet seems to be that you need to keep the partitions at 12. But it's expression-based, so it's a little bit more, instead of just defining a single column and a single rule on that column, you can actually define a more robust, more arbitrary partitioning strategy. I don't know how useful that is, but it seems like it could be powerful in several instances. Let's see. We'll go through this pretty quick. We've got about 10 minutes left. I want to leave at least a little bit more time for questions at the end. So some tips when you're working with MPP databases. And a lot of the challenges of MPP databases come down to system design. Figuring out, if you're not buying an appliance like from Netezza, you have to solve a lot of the hardware configuration, balancing trade-offs yourself. And the three major ones are network bandwidth, disk I/O, processors, CPU. And the answer for almost all of these MPP solutions is more. Like just, this is not, the other advantage of Hadoop is it runs on with commodity hardware. The MPP database boxes in your server farm are going to be probably the most expensive machines you have. They're always going to want the top of the line, everything and some. So network, 10 gigabit, cards for all the machines, maybe 2. A dedicated switch, so to make sure you're segregating the inter-network communication between these 24 or 36 nodes from the rest of your network. They can't be competed for network resources because the master node is going to mark things as offline when it can't detect them, and then you're going to have to recover them. You really need completely dedicated network for this. Sorry, ended up with that slide twice. Disk I/O, again, more. There are SSD solutions with MPP. Most people in the big data space, you're trying to trade off data versus speed. You've got CPU as one bottleneck. You've got disk I/O versus another. You've just got a lot of data. So you generally end up back with magnetic spinning disks in order to get the sheer volumes you need. If you've got SSD drives, it's really hard to have 20 terabytes of data on each machine with SSD drives. So you end up with disk drives, and you don't want, and if you've got to get 100 terabytes in there, and you can only put 5 terabytes per machine, that's a lot of machines. It's a lot of expensive CPUs. It's a lot of RAM. So it's a constant trade-off to find how high up to go. How fast can you make the disk versus how much data can you fit in there? And I mentioned this earlier, but I want to reiterate it again. This is another example of where you really see the fact that the scales are going up becomes something you have to deal with. Because now you're going to have failures. So as I said, we have a 24-node Greenplum cluster with 18 hard drives on it. While I was researching this, I found the Backblaze backup company has some interesting blog posts about hard drive failures. They have a lot of hard drives, and they posted a lot of numbers about different vendor failure rates. Their best vendors that they were listing were in the 2 to 3% range. And they had vendors that they were getting 10% annualized failure rates from. Big vendors, like famous, reliable hard drive vendors with annualized failure rates in the 10% range. But even just take a 3% failure rate. 24 nodes, 18 drives per node is 432 nodes. At a 3% failure rate, that's 12 drives a year. That's 1 drive a month. So you're going to have months where you're losing 2 drives a month. And so your RAID solution needs to allow you to swap hard drives without that being a big deal. Your cluster solution needs to allow you to fail over to different nodes when you have degraded arrays so that you can continue processing data quickly. It really becomes a problem of it's not the backup problem so that you hope you never need to deal with a lost hard drive and restore from your backup. Once you're talking about big data, you're going to lose hard drives. And you're going to lose a lot of them, and you're going to lose them all the time. And you have to have a solution that allows you to handle that. I believe Redshift automatically provisions a whole set. I think 30% of the data that you pay for from Redshift, they provision that many hard drives in secret on the back end in a RAID 5 or 6 array, and hot swap those in when the hard drives fail, because they're just going to fail. Hard drives are going to fail. Processor to memory, you're going to need a lot of that too. I think we run 128 gigabytes per node, a lot of RAM. And processors, you're going to need fast processors. The interesting thing there is that that's really how you decide how many nodes to create. So you've got 4 nodes. How many Postgres to install on each of those? Well, the answer is you install 1 Postgres per CPU, per true CPU core. So you might have 2 CPUs, each of which has 6 real cores, and you give 1 to each core and sort of ignore the hyper-threading. So to answer your question, some differences between the three of the big MPP databases. Greenplum has, I believe, if not the most full-featured SQL, it's very close. It supports UDFs. It has built-in analytics functions. You can run linear regressions using UDFs out of the box. It's pretty good as an ad hoc query cluster. It doesn't have to be tuned to be good. It can be good right out of the box with a pretty standard warehouse Snowflake schema. It'll be good for that. So if you have a general purpose, you want to give analysts something and you don't know exactly what they're going to want to do, Greenplum's a pretty good solution for that. It's extremely sensitive to hardware. I think that's true about all of these, but since I have a lot of experience with Greenplum, I definitely feel the pain of, everything's got to be perfect. It's got to be fast. All of the pieces have to be fast to make Greenplum fast. And it can struggle with concurrency. I think that's true, again, about a lot of the MPP databases, but you can't really run more than 2 or 3 large queries that are accessing a significant portion of your data. So the query times for a lot of these, if you're looking at multiple months of, just say, hundreds of gigabytes of data that you're trying to analyze to terabytes of data that you're trying to analyze in a single SQL statement, the query times are going to go from, it can return in seconds if you're not doing much, but if you're doing a lot, it can take 10 minutes, it can take 30 minutes. Some queries that we run take 8 hours to come back. And then it builds and sends data around and eventually returns 8 hours later. So concurrency becomes a factor. Like, you can't just open this up to your analytics group and say, everybody go nuts, fire off 20, 30 queries at a time. It's really going to bog down and it's going to start thrashing, and it's not going to do great. There are queue tools you can use to keep people from opening it up, but if you need to let 20 people all answer questions at the same time, it's going to be tough to do that in Greenplum. Vertica, columnar from the ground up, you don't get access to rows. You can't create a row-oriented table. Sometimes row-oriented tables really are the right solution. If you have updates, you might need a row-oriented architecture. It's just not available in Vertica. And projections, I'm not going to talk about those. Let's see. Redshift, based on a company called Parasail before Redshift. I think this is probably the most interesting MPP out there right now. It's still behind Greenplum and Vertica in its SQL support, but it's moving fast. They're adding features to it at a very fast rate. So it's going to catch up soon, I think, and be a really interesting solution. And it's in Amazon Redshift, it's in Amazon AWS, which makes it interesting economically as well. OK, so we have a couple tips. This is one we found. Stay away from distinct. At some point, this is Greenplum specific. Greenplum's going to fix this, but right now, you want to rewrite all of your distincts as group bys, which you almost always can. And then use temporary tables is the other tip I had for using Greenplum. I'm going to skip through and open it up for questions. Sure.
Can you talk a little bit about the advantages and disadvantages of the appliance software?
Sure. Most of the vendors are going to push you to their appliance if they have both available. In general, for the same amount of hardware, the appliance is going to be more expensive, but it's going to have been tuned by their experts. And then again, it comes back to the trade-offs we talked about earlier. Like, you probably are going to have to investigate this on your own when you're building. We did both. We took the EMC appliance and we benchmarked it against an equivalent number of machines that we built ourselves, and we benchmarked it against an equivalent cost of machines that we built ourselves. And we ended up sticking with the software solution because at the same price, we could have more nodes. And it ended up, even though their nodes were a little bit faster, we could have more, and it ended up being a net win for us. But that's going to depend on your problem. That benchmark might flow the other way in a different solution. So it's really hard to answer one way or the other. It's a lot easier to get support if you have the appliance. Go ahead. Yes, that's, so the question was, is the 36 nodes compressed? There's 100 terabytes compressed. That's compressed, yes. So uncompressed, somewhere around 200 maybe. According to Greenplum, we're getting a 3x compression, but that's based on some kind of fuzzy estimates. But we're seeing between 2 and 3x. I've seen tables get 10x, and in a columnar-oriented database, that's not at all unreasonable to get 10x. But what we're getting as stats from the machine are in the 10x, are in the 2 to 3x range right now. It is columnar. I think columnar databases also need to be ordered a specific way to get huge compression. Like if the columns themselves are ordered so that like data is together, it's a lot easier to get those 10x, 20x numbers. Go ahead. Mm-hmm. Yep. Sure. For structured data, so for unstructured data, MPP is probably not your solution. Is really like you're going to need to give that data a structure. If you just dump it in, if you try to use your MPP as a big key value store, it's probably not going to work great. It really, all of its advantages come from knowing about the structure of your data. So, so it's not a great solution if you have unstructured data. You're going to have to pre-process it into a system that has structure. And if you can't do that, Hadoop is a much better solution. I think we should, I'll be around if people want to ask questions later. But I want to not run over by too much. Thank you.